today we're going to talk about how to do math in general in NARS. So we have said many times that NARS is non-axiomatic, which is based on my working definition of intelligence as adaptation under the assumption of insufficient knowledge and resources. So a major difference between this approach with the traditional approach is in such a system, knowledge does not really try to describe directly the world or the reality. Instead, it directly describe or summarize the system's experience, which is how the system interacts with the world. So what I mean, the so-called experience-grounded semantics, I think there are two major points. One is respect to truth. Okay, in this case, clearly truth is not a yes, no, or true, false situation anymore. It's a matter of degree. And also meaning is not a fixed thing anymore. A concept does not have a real meaning or true meaning or whatever you call it. Instead, the meaning change over time. So that directly come from this AIKR principle and adaptation. And also it take a different attitude toward what we call inference. It's not theorem proving that go from truth to truth anymore. Instead, it's some kind of concept substitution. So you use one concept as the other to a certain degree. So, well, you have seen this many times, right? So the system's memory is nothing but a conceptual network where each concept has a name, which we call a term. And so there are also different types of terms. There are some linguistic terms which correspond to words in natural language. And there's some perceptual terms that correspond to your direct sensation or perception. There are operational terms that depend associated with what the system can do. And also there are some private terms which is completely within the system, like what I use, just ID, which does not have a public meaning. And also there are compounds of them so that you can build a new one using a structure of the existing ones. Here also we can further distinguish two groups of them. You can call it exterior or interior. It depends on whether you have something that directly corresponds to it in the system's experience or not. And also you can see here there's several basic type of meta-level relation which we call copular in the system. In this diagram, we have the blue one that's called the inheritance relation, which form a hierarchy, and also a similarity relation, which is kind of like two-way inheritance. Okay. So that's about the meaning. So the meaning of a term is given by all of its relations experienced by the system. And for the truth value here, the truth value is actually some kind of evidential support in experience. You'll see again, this I have shown many times. You define positive and negative evidence. Then you use the positive and negative evidence to define a two-dimensional truth value. Okay. Both meaning and truth change over time. It's not a yes-no thing, it's a matter of degree. So everything so far, you're already familiar with, most of you. So starting from this slide is really the new idea. Okay. So on one hand, as the name suggests, the system is completely non-axiomatic in the sense that there is no absolute truth, there is no fixed meaning. But on the other hand, actually the system is moving toward an axiomatic system. Because under the assumption of insufficient knowledge and resource, the system itself try to reorganize its own knowledge. In this process, it assign a priority value among its concepts and knowledge. So in this process, you'll see what is favored. Even though every belief is true to a degree, the system actually favor the beliefs with extreme truth values, which is kind of like as close to binary as possible. Okay, you want this to be basically true or basically false. You don't like the thing which is always kind of like say always in the middle. The same thing for meaning. Even though we allow all the meaning to change over time, the system favors concepts with a relatively stable core meaning. Okay. On the other hand, some concepts meaning change too much, the system will not like it. Also, the system prefers simple knowledge with many derivatives. That is, you don't have to remember everything, you just remember a small part of it, and you derive the other thing from them. Okay, so this tendency actually is a tendency that moving to an axiomatic system. Even though the system is non-axiomatic, in principle, you want to have this tendency, you see, as I mentioned here, because you want to have certain simple, consistent, and efficient decision and actions. So in this sense, that axiomatization is a good thing. It's just that you don't always have it, but you make your effort to that direction. So there is an interesting result is in this system, there's always two opposite tendencies going on at the same time. Okay, for the system itself, it will try to organize its knowledge in this network by focusing on the stable and clearly defined sharp relations. On the other hand, it's in a reaction with outside environment, always challenge the current organization and try to destroy it. Okay, wherever you summarize some pattern, then you run into new evidence, say, oh, that's not the case. Okay, oh, this is a counter example, and so on. So both are rational. Okay, you don't want to fix your belief, say, whatever happens, I just believe what I have got so far. That's clearly not adaptation. But on the other hand, you don't want to say everything goes, so that every concept is equal. Okay. So that actually explains why, even though I think non-axiomatic reasoning is more fundamental to AI, axiomatic reasoning is rational and it's actually very valuable. Okay. So how to get it? You see that there are also several different types. The first type, we can call it a concrete axiomatic model. Here I'm using model, system, theory, more or less mean the same thing. Okay. This can be done through idealization process. For example, for certain beliefs, if they're certain enough, okay, I mean the truth value, you have a very high or very low frequency, which means it's close to 0 or 1, and the confidence is very high. Okay? You kind of like take it as a fact or truth, even though you know it's true to a degree. Okay? So you idealize them into axioms, which means it's a binary truth, or you call it postulates, or you call it your assumption, or whatever different name. It basically means the same thing. It means that I know it's a messy, but I idolize it to be binary to make my thinking and inference easier and more clear and easier to follow. The same thing for concepts. Okay, a concept by definition is the meaning is defined by all of its relations. Okay? But in reality, you don't want that complicated situation so that to always think about a relationship, which is practically almost impossible. Okay, so for certain concepts, you can say, okay, among say the thousands of relations I know, I think there are 5 of them, which are the most important one, which I call them the core meaning or the essence of the concept or whatever. And you take the other things as secondary or non-essential. Okay. So in this way, you can get some idealized concepts. Then what? Then from those basic concepts and the basic propositions or whatever you call it, you can recursively define the other concepts, also use binary relation, and you can recursively prove the other theorems, starting from your axiom. Okay. So this kind of system, we can call it some kind of convention-based semantics. This is kind of like the arbitrary of what we call experience-based semantics, because here convention can be consciously maintained. So that's my commitment. Okay, I don't care what have happened and what will happen. I will just take those things to be true for a certain purpose. So this convention-based semantics and experience-grounded semantics have a fundamental difference because this can be fixed and also can be made binary, can be idealized. Experience, on the other hand, you have no control. You're open to new experience, whatever. Okay. So this is, for me, that's where math come from in the first place. So example is Euclidean geometry, which clearly has experience foundation. It comes from people's experience. But after you idealize it into an abstract model or axiomatic model, you make the commitment that I will just take those things to be true. And their relationship with experience become secondary and also not essential. Okay. So this is, for me, the first step from non-axiomatic to axiomatic, in a sense that it's kind of like you capture the relatively stable part, you idealize it. Then there is a second step, also interesting, that is you move even further by kind of like completely cut off the relation between the concepts in your model with your experience, which will give you formal system. That's a formalization or a symbolic system and so on. Okay, so you make them as some kind of abstract framework or template, which is by definition completely disassociated with empirical knowledge. Okay, but of course that's where it comes from, but and that's how you use it. But that's a separate step. You use interpretation to ground the symbolic concepts to the empirical concepts. But the difference between this situation with the previous situation is not only the empirical relations are optional, but also they're not fixed. You can move from one interpretation to a completely different interpretation. So under different interpretations, your symbols can have completely different meaning with respect to your application situation. Okay. So in this scenario, we say, what do you have? It's not a concrete model. Instead, it's a formal model. So an example is graph theory, right? You can see that graph theory and geometry is kind of similar, but geometry has some kind of intended interpretation, intuitively speaking, even though you can interpret it differently, but that's rare. Graph theory, on the other hand, is completely up to you to say what is a node, what is an edge, and what is a path, and so on. Okay, they can be mapped into very different things. So in that sense, this is more, or you can also say formalization or formal or abstract is a matter of degree, but at least we can say this is more abstract than geometry in that sense. Okay. So in terms of a picture is something like this. Again, this network is what I show as the conceptual, is the empirical concepts, which form a network which has a boundary which will interact with the outside world. But when you're moving away from the boundary, the concepts get more and more abstract. Okay? But still, in principle, is still indirectly related to your experience. So it's not abstract in absolute sense. But on the other hand, you see that the frames I draw here is kind of like floating above this network, which is what I call formal model. Okay, and this model, you need to give it interpretation, which is the thin line I draw here. By map them into the counter-rated relation, you can see that I will say, okay, for this given situation, I can take my empirical concepts as the abstract concept in this model. And what's the benefit of that? The benefit is in the abstract model, you have already derived a whole bunch of theorems from the axioms, which is your starting point. And the derivation is a proof in the sense that if the axioms are true, then the conclusions are true, okay? Or the theorems are all true. So after this mapping, as far as you can make such a mapping, you get a whole bunch of truths about your domain, okay, altogether. So that's and you can make different mapping so that you can use the same model in different way. That's what I summarize here. Another aspect of this process is what we call abstract operations. So what I just said is basically still declarative knowledge. How we can analyze declarative knowledge into abstract axioms and theorems. Similarly, for procedural knowledge, for what the system can do, there are also an abstract version. Many mental operations abstract in the sense that they can be applied to different situations, so that be applied to different empirical concepts to actually correspond to different relationship and different procedure, even though in the abstract form, they remain the same. Okay, they're independent to any specific interpretation. And also, operations are binary by nature. That's a also very interesting difference, which we discussed before. So to me, that belief is always a matter of degree. The actual belief is always a matter of degree. Even though so far you don't have counter evidence, you always need to be prepared for counter evidence in the future. On the other hand, operations in general or in principle is a binary. It's something either you do or you don't. Okay. Of course, some more complicated operations have parameters which you can say, okay, I will push, but I will not push very hard, right? So there is a matter of degree, but that's a secondary, and that also can be captured by the use of parameters or arguments. But within the system, when you're making decision making, doing decision making, you either pursue a goal or you don't. It's a binary thing. Okay. So I think that's another important reason for why people still prefer binary truth value, even though beliefs in general are true to a degree. Okay, because eventually you need to do something or not. Okay, so and also each of them can be used according to conventions, which decide under what condition this operation can be carried out and how to interpret its consequence. So this is the procedural part in axiomatic theories, which also can become coordinated or organized into a system themselves. There are a lot of discussion about this in Piaget's work with respect to a formal operation, which I completely agree. For example, the arithmetic calculations, which is a system of operations which have relationship among them. So also similarly, you can map abstract operation into physical operation, just like the procedure and the declarative knowledge. So that part is basically my philosophy of mathematics. That's how I see mathematics and axiomatic system and what's their role in cognition and intelligence and how they're related to non-axiomatic system. Okay. Now let's talk about some detail. Okay. How to do that in NARS? First, truth value. Actually, previously, I guess many people have the guess, and also I actually thought that way, is we kind of like use the extreme case of the current NARS truth value as a binary truth value. Like, for example, if you make both frequency and consequence and confidence to 1, so that's kind of like absolute truth, which is correct, which is still the case, okay, conceptually. But I'm not going to use that for the purpose we're talking about. Instead, we introduce concepts like true and false as either, in this case, it will be like adjective. Okay? We use them as features or properties of proposition. I do not say, truth value is 1, 1 is true. I just say this is true. To be more accurate, actually, this is always model dependent, meaning that when I say true, I need to mention in which model. It's true in Euclidean geometry, or it's true in number theory. Okay, but for here, just to make things simple, I will just say that true and false, you can introduce them as a meta level or higher order feature of proposition. In the same spirit, you can see we can define something. A definition, accurately speaking, is actually a relation. It will relate a term to a compound, which is, this is what you want to define. Okay, this is how to define it using other words, typically a certain combination of other words. So you can match each term with its definition, and we will just call this to be a definition or something, or convention in a system. Again, now that's become a narcissist term. So within an abstract model, your reasoning typically start from the axioms which are taken to be true. You see, again, this true is a convention. Of course, it has its empirical reason why you take this to be true, but not that one. But that's a separate story. Okay, as soon as you make that selection, you make this commitment, and its truth will cannot be challenged within the system anymore. That's your commitment or your conviction. Okay, you start from there, then you begin to do reasoning. And here, once again, the inference rule within this model should not be confused with the inference rule of Narcisse. Okay, they're not the same at all. They don't even need to be similar to each other. Instead, an inference rule of a specific abstract model can be described either declaratively as an implication statement. Say, if these things are true, then this conclusion is true. Okay. And this, I roughly represent it in this way, but the detailed description, you should use the word true or false or something like that. Or you can describe it, or you can code it procedurally as, this is the format of NARS operation. Okay, you can define it as an operation, you call it derive or detach or whatever, which takes some premise as the input, or that's what we call independent variable, right? And derive a conclusion, which we call it dependent variable. Okay. So again, in NARS, we can do it in this way. And then eventually we want to derive some theorem, which will also be true within that model again. So what is the relationship between this thing and the empirical beliefs? Meaning that do we have still have the Narcisse truth value attached of each of this? Yes. Okay. So they coexist within the system. Yeah. So you can say, I believe this to be true to a certain degree, but this true and that truth value are different things. Okay, this true or false is with respect to a certain model, and truth value in principle is actually kind of like the system's feeling. or degree of truth is kind of like an internal feeling according to its own experience. Sometimes you can even have situation, something I know is true, but it doesn't look like true to me somehow according to my intuition. Okay, we can have that situation in the system, like a counterintuitive conclusion, or something like hypothesis is typical of the situation. I guess this is true, but I cannot prove it so far. Okay, so you don't have a truth value in this sense, but you can have a truth value in the narcissist sense that, for example, I have tried it many times, it works. Okay, but it's not a mathematical truth, which you need to obtain by a proof. So we can have both of them coexist. So now is if we take those abstract model into the system, then if we focus on them, what kind of inference activity we will have in NARS? Compared to the current situation is of the reasoning non-axiomatic, according to the now inference rules. I will say in general, there's 3 tasks which we discussed before within our own team. Okay. One task is reasoning or inference completely within abstract model. This is typically a theorem proving. Okay. The second one is to apply it to a practical situation. Here you will have interpretation involved, and you will see there is a mixture of axiomatic and non-axiomatic reasoning. And finally, where are the abstract model come in the first place? Okay. So how to get a pure abstract model or even a formal model from a system's experience? Okay, I think there's 3, of course, related, but still are different topics. So I'm going to quickly go through each of them. Abstract reasoning or theorem proving is basically what I have already said, but in this reasoning, you see, you can only use the model-specific definition, axioms, and inference rules to reach your conclusion, to prove. All the theorem proving start from definition and axioms and should use the inference rules allowed in that model. Okay, and on the other hand, the empirical beliefs of the system still play an important role. They provide hypotheses, heuristics, and the intuitive guidance. Okay, this is also a topic discussed a lot in the past discussion about philosophy of mathematics. It's whether empirical knowledge matters. Well, everyone you have done math, of course, know that it matters. Okay, very often your intuition, your inspiration come from something outside of the mathematical model. But on the other hand, you cannot use that as an argument. Okay. Your argument still have to be built within the model. So we will need both. And now we see that in this NARS environment, we have the hope or the possibility to do that. Okay. So again, it basically means that you use your experience to guide your abstract reasoning, and you will need both of them to do theorem proving. Just so this approach will be very different from the traditional work in theorem proving, which is completely based on, say, algorithms or axiomatic methods, and completely ignore the role of empirical knowledge in the process, or almost completely ignore. Okay. So another thing it will provide is you see that NARS serve as a universal methodology for any kind of like arbitrary abstract models, in the sense that you can teach it propositional calculus, you can teach it probability theory, you can teach it whatever you want, just like how you teach a human a mathematical model. But of course, there is no guarantee that NARS can learn it successfully, just like sometimes we run into trouble when we learn a complicated system. Anyway, that none of those logic is necessarily built into the system. You need to teach it. The built-in thing, NARS, with respect to those models is a matter logic. Okay. So it will decide how to represent the propositions in that model and how to code or represent the inference in that model in a universal way. Not necessarily the most efficient way if you just want to use that one model. But this advantage here is we can teach it any math in principle, okay, according to what I just said. So this is the first topic. The second topic is, if you have already learned a mathematical model, abstract model, you can do theorem proving. How can you apply it to a practical problem? To me, the first step is to recognize the similarity between empirical problem and an abstract model. Okay? We know that every mathematical theory has its applicable situation. You cannot apply any model to any problem. And this judgment itself is not part of math. It's about how to use math and in which situation one specific math theory can be used for. Okay? There must be some similarity between the relations captured in a model and the relations you're facing in your current problem. And also, in principle, you should verify the precondition for the model to be applied, which is very often omitted by people. But we know that without that, the conclusion doesn't make sense. Okay. Then what? Then you create an interpretation. Within NARS, interpretation is nothing but a similarity statement. You say that for my purpose, current purpose, I take this abstract symbol, for example, that's X, to be similar to a concrete concept I'm using to describe the situation. So you know, because of this similarity statement, we can do reasoning like analogy and so on to map the conclusion within the model to the conclusion outside the model. Okay. So you'll see, very roughly speaking, what you're doing in this kind of application work is a combined axiomatic reasoning and non-axiomatic reasoning. Here I'm using a very simple color code to show that. The blue step is something happened within a mathematical problem. The green part is how it's related to your empirical problem. Okay, like you have this A is a type of P where both A and P are your empirical concept, and now you realize or you recognize or you believe this P is basically can be mapped into this capital P, which is a formal model. And also this $X, you know, again, is a variable term. In NARS, it can be unified or instantiated with any arbitrary concrete concept. In this case, is the lowercase a. Okay. Again, of course, there's something like additional conditions you need to check, but I will just, this is a similarity relationship. Okay. So I will just take this empirical thing to be this formal thing to a certain degree, and this one will imply that, and under the same interpretation, I'm going to map it into a concrete conclusion in my domain. So in this way, I derived A is also is a type of Q, from A is a type of P. So from this green to green, I'm actually talking about the relations between my empirical beliefs. But this inference use axiomatic reasoning somewhere in the middle. So to make this efficient. So that's kind of like a very, very rough description about what's going on when you apply it. Finally, how to create an abstract model in the first place. Well, that's basically what I said. In theory, it sounds simple. You just need to, among your beliefs or empirical experience, you need to identify there are some generally applicable conceptual structure or pattern. Okay, you see, okay, the relationship among this group of concepts in this domain and another group of concepts in a very different domain actually have the same structure, if you draw some concrete empirical relation, but focus on something else, okay, some other relation, and then you give them abstract meaning. So technically, what we should start from, that's what we already have in NARS. For example, those of you who are familiar with the inference rules, you should know what I'm talking about. The variable introduction. Okay, we introduce some variable term. What makes variable term different from constant term is not because the other term does not change its meaning. Every term changes meaning. Okay, variable term has a special property that it does not specify any concrete concept. It can be used flexibly to map into different concepts, to be instantiated differently. So that to me is the beginning of mathematics. And we can use that to do hypothetical inference. So we can talk about if this is the case, then blah, 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 blah. And the condition does not have to be true. Okay, it can be counterfactual, it can be factual, it can be completely abstract. And there's actually no difference as far as hypothetical inference is concerned. Okay. Also, we can have higher order statement, as we have seen before. We can say that this statement is true, or this statement is my convention, this statement is my assumption, and so on. Okay. And also we have mental operations. We can do something within the system. We'll just say, we'll just take this one and that one to be equivalent in truth value, and so on. So all those things are already there. But of course, to actually build a mathematical model, you need to deliberately do axiomatization and formalization, as I described before. You need to abstract a relatively stable thing and cut off more or less from experience. Okay, and this is not always easy or can be successful. So it demands special experience and expertise. What I mean is this is not really completely a logical thing. Okay, actually, only a very small number of human beings in their lifetime create an acceptable mathematical model. Okay, but if you fail to do that, it doesn't mean something's wrong with your logic. To me, actually, it has more to do with your experience. You need to, do. So here we also, mathematics is a special domain. We need a special training. Okay? It does not mean that you need to change your meta logic, but you need special expertise and to make it happen and successfully. So actually, I'm not really expecting NARS to be easily become a mathematician in a sense that it can develop its own mathematical model. Even though I think that's a logical possibility, I don't think we need a different logic for that to happen. But we need to know how to teach it to do that. But that is very, very complicated. Okay. But we can try if we want. So that's basically about the 3 tasks. Now, again, let me be a more concrete, okay, talking about where to start. You see that this presentation is based both on my previous knowledge or ideas about math, as well as based on our recent experiment within the team. A lot of work has been done by Patrick, by Tangrui and Hongzheng recently, which is also combined into my presentation here. Okay, so how to count the numbers? First, conceptually, counting is a mental operation. Okay, that decides the size or cardinality of a set, which in NARS is called extensional set. Okay. And the result is a number. What is a number? We can introduce another type of term, just call it a number, which will refers to number concept. Okay. And how to get a number? Well, here, for some small numbers, I think we can directly get it from the experience. In this case, that it corresponds to what? It corresponds to repeated components. Yeah, extensional set. For example, I say there are two apples. I recognize this is an apple and that also is an apple. Instead of two, I can say there is this apple and that apple. I can do that without introducing numbers. Just directly talk about the objects under the condition that the number is not too big. Okay, so we can do that. And also, technically, we can actually directly calculate or count the number of components in a compound, of course. That's already there, right? We haven't turned it into a numerical term. And also, when you build, you see this is something we probably want to try. If we in the past, if we have Apple 1, Apple 2, Apple 3, we will just build them as an extensional set. Okay. In the future, we may want to directly turn it into a number, say instead of say Apple 1, Apple 2, Apple 3, we'll just say 3 apples. Okay, that's technically not too difficult to do. It's just previously we don't have a numerical term. And the more interesting thing happens when, for example, if we want to do it in a robot and teach a robot how to count. You see, this is nothing but a situation where we are still talking about extensional set. You need to have a category. You don't count everything. You always count objects of the same category, where the category can be introduced at runtime for that specific situation, right? You can count apples, you can count fruits, you can count objects, then the scope will all be different, even in the same environment. So what happens within NARS will be, you see, it's a repeated recognition. If I say I want to count apples, I need to recognize whether this is apple and this is apple, that is not apple, so that will not be counted. Okay. So as soon as each recognition gives you a yes answer or close to yes answer, you record that somehow. Okay, so this is directly related to repeated recognition or repetition of a certain event within the system. And how to remember, how to count the result, again, there are different ways. We can use the internal successor relation, which also we tried some simple example before. So we know that 2 is a successor of 1 and 3 is a successor of 2. You know, wherever you increase the internal counter, you just move along that relationship. You can do that by reasoning. Or you can use an external counter. You use some tool to help you, like fingers, rows, or now we can have a small program, right? We just call it. So we don't have to really ask a robot to count its fingers, and just because some of them doesn't have any, but they will do similar things in principle. Then more complicated situation, also we recently discussed about how to handle functions. Okay. Function in NARS is a special relation. Compared to other relation, the difference is you, among all the arguments, you take one as the output or dependent variable, the others as input or independent variable. You will decide the value of the dependent variable according to the value of independent variable. And you force the mapping into a many-to-one mapping. Okay, if there's multiple candidates, you need to use the choice rule or some rule to decide which one is the result of this function calculation. How to do that? Again, if we limit ourselves at the beginning to numerical function, again, we can do it in 2 different ways. One is we implement it by an operation, like computable functions, right? Or we can do it by inputs. Okay, both should work in principle. And a function can be treated as a number so that you can define functions recursively. Okay. So we should be able to do that. And how about measurements? This will be similar. We already know there are two ways to handle measurement so far. One is to roughly use the tooth value itself to do the job. Okay, just that you see, I have discussed this kind of thing many years ago. So like big and small, we take it as a relation. We will see that when we say Tweety is a small bird, we actually say that Tweety is smaller than the other birds. So we will have positive and negative evidence, then we will have tooth value to kind of like indicate Tweety's quartile in terms of relative size within the group, the size of bird. So we have been using that for a long time, okay? But that's a rough measurement. And now we have numerical measurement. We can directly introduce concept with numbers in it. In this case, we can have numbers and the units of the measurement combined as a concept. So we can just say that the weight of Tweety is, is this amount using that unit. So this is also related to counting. So it's kind of like how many of those units will give you equivalent weight. So not going to go into detail. And also we can roughly replace a numerical measurement with linguistic descriptions, roughly. So that's what the fuzzy logic people have been doing to a certain degree, in a certain context. Of course, all this are context sensitive, which I'm not going to go into detail. So conclusion. I think axiomatic models can be naturally grow out of NARS, even though NARS is not axiomatic in principle. Okay. Instead of using another kind of like hybrid approach with axiomatic and non-axiomatic, some kind of combination. And the axiomatic model can have its own logic that's very different from the non-axiomatic meta logic. There is no contradiction there. And this is a big claim, okay? I think in principle, the current design of NARS is completely compatible with the adding of mathematics into it. So there's only probably some small revision, no major revision. It's basically an extension. That is, we need to add more things into it. Also, this adding is mostly not at the design level, but more like the education process. Okay, you feed it proper Narcisse sentence to make this happen, instead of change the source code. Okay, so these are my previous writing, which are related to the basic idea. But the details are more recent development. Okay, that's all.